So the next topic which we are going to start is magnetic force on the charged particles. So we just discussed that how a moving charges or current produces magnetic field and how much is the amount of that. Like we just found, like how can you get the magnetic field due to various current distribution or moving charge distribution. So now if a moving charge is there, then how much force it will experience. So we just discussed that like it is moving charge which produces the magnetic field, and inside the magnetic field, if there is moving charge, then it will experience a force, right? So let us just discuss about that particular force. So if Q charge is moving with a velocity V vector enters in a region, okay, where the magnetic field is B, then it will experience a force, okay. Now this force experience is given by this expression, and this expression is important. Force is given by Q V cross B. So here it is V cross B. What does that mean? That means that direction of this force is perpendicular to V as well as perpendicular to B, right? So it is going to be perpendicular to V vector as well as B vector. Means what does that mean? It is always perpendicular to velocity vector. So if velocity vector is the direction of motion. So if force is always perpendicular to the direction of motion, it is not going to produce any acceleration along the motion. Hence, we can say that the work done will be zero because, or power will be zero. Power is what? F dot V. Okay, so force and V are perpendicular, so F dot V is always zero. No power will be generated or no work will be done during the motion. So what can we say? We can say that kinetic energy of charged particle only inside the magnetic field. Okay, electric field is not present at all. Can never, like a single magnetic field cannot change the kinetic energy of a moving charged particle. It can only change the direction of it. It can never change the magnitude of its velocity. Now, the Lorentz force. This is our next topic, the Lorentz force. What is Lorentz force? So Lorentz just tells that if there is a charged particle into magnetic field as well as electric field, okay, then the net amount of force is called the Lorentz force, and it is given by the expression Q V cross B plus QE. If you see this force, there are two parts, QVB and QE. We have already discussed this force. This is nothing but electric force or electrostatic force. What about this? This is nothing but magnetic force. So for electromagnetic force is basically Lorentz force, and here the direction is also given. The direction of the force due to electrostatic force is in the same direction as electric field, but direction of magnetic force is perpendicular to velocity vector as well as perpendicular to magnetic field vector. So it is, the velocity is in this direction, the magnetic field is in this direction, and to get the direction of V cross B or QVB or the force, you need to do the cross product. So just move your or curl your fingers in the direction of V and then turn them towards B. Then your thumb. So I'm just turning keeping all right. I'm using my right hand. Then I'm moving my fingers in the direction of V and then turning them in the direction of B, like towards this angle. So I can see that direction as above. So this is my magnetic force, which is in upward direction, which is perpendicular to V as well as perpendicular to that B vector as well. One more thing is that if the charged particle is stationary, the velocities will be zero and hence no magnetic force will act. So we'll say magnetic force, there are two essential conditions for magnetic force. One is there must be a charge on the particle or neutral particle. Q will be zero and this will not move. And the second thing is the particle must not be stationary. It must already be moving. Then only magnetic force can act on it. And this combined force, electromagnetic force, the electric plus magnetic force is called the Lorentz force. So this is the Lorentz force which is there on a charged particle in the presence of magnetic and electric field. Now we are going to talk about the cases of projection in the magnetic field. What happens when a charged particle is moving in a magnetic field? This is the case number 1 where velocity is not zero. If velocity is zero, then magnetic force won't act, right? Particle will remain stationary. So first case is the velocity is parallel to B vector. We can also say that in this direction, the direction of magnetic field is there. There is a charged particle which can move either along the magnetic field or opposite to the magnetic field. In both the cases, the angle between B vector and V vector is either 0 or 180 degree. So if that happens, we know that the force, the magnetic force is nothing but Q V cross B. And if we are just writing the magnitude of this magnetic force, electric field is not present, right? So that is nothing but QVB sine theta. And if theta is either 0 degree or 180 degree, or we can say pi, 0 or pi, then this sine theta is 0 and hence the force is going to be 0. So if force is not acting on a moving particle, then what will happen? It will remain moving in the same direction with same velocity, or we can say it will perform uniform motion, right? So the particle goes undeflected, undeviated. It will remain moving with same velocity in the same direction. Nothing is going to happen in this particular case. Now next case is what happens if velocity is perpendicular to magnetic field. So if that happens, now if velocity is perpendicular to magnetic field, then particle is going to perform a circular motion. Why? First thing is the force provided by magnetic field is always perpendicular to the velocity, and if force is always perpendicular to velocity, then that is only possible in a circular motion. So here as particle enters, eventually it performs a circular motion in the magnetic field, right? So here we will say that force, how much force is acting? QVB sine theta, and sine theta is 90 degree. Initially I am talking about, initially the force is QVB, which is perpendicular to velocity. Let us just understand how this circular motion is happening. So when this particle was entering, here the direction of magnetic field is this, in this direction, right? So this is the direction of magnetic field. The charged particle is entering. This is a negatively charged particle. So this is a negative charged particle which is going in that direction, which is like into the screen. Now get the direction of force, that is V cross B. So this is the direction of my V vector. Do V cross B. So when I do V cross B, the direction is below. But since it is a negative particle, we discussed that force is nothing but QVB, V cross B. So V cross B is downward, but the charge itself is negative. So direction of force is going to be upward. Everyone is getting that? If you do V cross B, right? V cross B, V is into the screen, and cross B, turn your finger in the direction, that direction. So you will say force is downward, but that is for a positively charged particle. For a negatively charged particle, it is other way around. So force is going to be in upward direction. And as the particle is moving in this direction, it will eventually perform the circular motion. So once it performs the half circular motion, let's just again have a look at the force. So here the direction of velocity is out of the plane, right? So do V cross B. V is out of the screen, cross B. So out of the screen is like this, cross B. B is like in this direction, and then you will see up. Then do the reverse because charge is negatively charged particle. So downward. So here the force is downward. Again, when you see this is again towards the center of the circle. So further circular motion will happen. Let us have a look at one more position. Here the direction of velocity is downward. The V vector is downward. What about B? B is still that way. So V, I am doing just V cross B. So you can see the force is outside, but since it is negatively charged, so force will be other way around, and eventually it is other way around means into the screen, which is towards the center. So as particle is entering, due to this force which is behaving as a centripetal force, at each and every moment it is perpendicular to velocity, and it is making sure that it is always towards the center for that circular motion. So now at this particular point it was acting towards the center. At this point also it was acting towards the center. So at each and every point, the force QVB, which is perpendicular to velocity, or the magnetic force is perpendicular to velocity, and we can see that this type of circular motion is going to happen. So particle will enter it and eventually it will rotate. If this was a positively charged particle, then what would happen? If it will enter like this, it will perform a circular motion, but in a direction which is just opposite, other way around. This is going up and performing a circular motion. The positively charged particle will go down and perform a circular motion. So circular motion is a fine thing. Like circular motion is a guaranteed motion when V is perpendicular to B. Now, let us just have a look at the parameters, the mathematical things which are coming to our exam. So, here the force is always perpendicular to velocity and it is performing a circular motion like that. So, first thing is the required centripetal force. This force, who is providing this force? The force is provided by magnetic force. I'll say QVB sine theta to be precise. The magnitude QVB sine theta, but theta is always 90, right? So initially it was 90 and then it will remain 90. So only QVB or QVB sine 90 is equal to mv square by r. And when we do that, this equation can be solved for radius. So we can get that how much is the radius of that circular path. So radius of that circular path is nothing but mv by qb. This is an important formula which you need to remember. Okay, so radius is mv by qb. What is m? M is the mass of charged particle. What is v? V is the speed, not the velocity. I'm finding the magnitude. So it is speed or magnitude of the velocity. And what is q? Q is the charge on charged particle without sign. If it is a negatively charged particle, the motion will be other way around, right? If it is positively, for it is anti-clockwise, then for a negative it will be clockwise. Direction would change, the magnitude will not change. And B is the magnetic field intensity or magnetic induction. Now, next parameter which we are going to do is angular velocity. So angular velocity omega is nothing but omega is V by R. And if I say V by R means, so V is, let's say, speed. And what about radius? We just derived an expression for this mv by qb. So this qb will go in the numerator and v will cancel out and we'll get qb by m. So this is my angular velocity qb by m. So angular velocity is given by qb by m for this particle which is performing circular motion because it had entered in a magnetic field where its velocity was perpendicular to the magnetic field. Now, time period is 2 pi by omega, and omega we already found it is qb by m, so m will simply go in the numerator. We'll get 2 pi m by qb. If you see this, see, time period is not depending on the speed of the particle at all. Here the velocity, time period or omega, both are not depending on the speed of the particle. Speed of the particle does not matter. So if a question comes, they say a proton and a helium, they are entering into the magnetic field with a different speed. Okay. Now, the time period is going to be directly proportional to their mass upon charge. The velocity is not going to play a role in that at all, while the radius is affected by velocity, charge and mass, all three factors. Then the last is the frequency. Frequency is 1 by time period. So it is qb by 2 pi m. Now, if we see all four factors together, so these were four factors which we had discussed, that radius is mv by qb, the angular frequency is qb by m, the time period is 2 pi by omega, so 2 pi m by qb, and frequency is reciprocal of that qb by 2 pi m. So here we are going to discuss, there is a particular case, and this case is what will happen if a charged particle is just going to enter a magnetic field. But here the magnetic field is limited to this region. This region is having a width of d and length, which is basically length we are not talking about as of now. Their length, they can limit the length as well in the JEE. So we are just discussing a case where they are limiting the width of the magnetic field. So here a magnetic field is lying in this region only. Now this charged particle which is having a charge, a q and mass m, is entering with a velocity v. As it enters at this particular point, what will happen? It will experience, as soon as it enters the magnetic field, it will experience a force. How much force? qv cross p. And it is a positive particle, so do v in the direction v, turn it towards the direction of b. So that is into the plane. So I am curling my finger into the plane. I can see force is upward. So as soon as this particle comes here, it will experience an upward force like this. So as it is experiencing upward force, it is going to perform a circular motion like that. But what will happen if before it performs the circular motion, it has to go out? So it is performing a circular motion like this, and before it performed complete circular motion or semicircular motion, then it went out that way. So once it reached this region, it will go out tangentially, because again till here the force was acting, but as soon as it comes to that particular point, then no force was acting at all, so hence it will go tangentially in that particular direction. How can we get this angle theta? So for that, what I'm going to do is, let us say this angle is theta, and since it is going tangentially, this will be 90 degree. This is radius of that circle, right? So this is 90 degree, this is 90 minus theta, so this is going to be theta again. What equation I can write is, if for this particular triangle, I can draw this triangle, I will say this length is r cos theta and this is r sin theta, and we can say that r cos theta must be equal to d. So r cos theta, that must be equal to d, and from here we can write cos theta as d by r. The expression for r we already derived, right? It was mv by qb. So d by mv by qb, and qb is going in the numerator. So this is an expression for cos theta. Once you do inverse of this, you will get the angle at which it is going to be deflected. So initially it was in this direction, deflected by an angle theta. Theta is given by cos inverse of dqb by mv. What is d? D is the width of magnetic field. There are various cases. The d, if d is lesser than r, then this thing is going to happen. If d is greater than r, then cos theta will be basically greater than 0, which doesn't make sense, right? So if this width is greater than r, what will happen? If this d is greater than r, it will be able to turn back. And now that depends what is the length of the magnetic region. If length is sufficient, then it will perform complete semicircular motion and eventually come out from here, right? So it can perform semicircular, it can perform a partial arc, right? It can perform any type of motion. One more thing which can be asked is, for how much time it is remaining in the magnetic region. So we'll say, once we get theta, if theta is known, then we can say that how much distance it has traveled. The time is nothing but distance traveled upon velocity or speed. We know that speed is not changing, right? So it is performing the motion on a r. This distance is nothing but r theta. So distance traveled is nothing but r theta, and the speed is nothing but v. And what is r? R is mv by qb. V will get cancelled out and we'll get m theta by qb. And this is the time it will spend inside that magnetic region. Again, here if you see, this is not depending. See, the theta depends on d, right? So depends on d, theta depends on d, and time depends on theta. So they said time again depends on this d. So this d must be given. Then we can do various things like finding the angle of deflection, finding how much time it is remaining inside the magnetic field and all. Now, next case number 3 is angle between v vector and b vector is theta. But this theta is neither 0 nor pi, means the v is not parallel to b. 0 and pi are cancelled, and theta is also not pi by 2. So means the v is also not perpendicular to b vector. In such case, what will happen? So let us just discuss here. So this is my north pole, this is my south pole, okay, and the magnetic field is from north to south between two poles, and I will say that there is a charged particle, positively charged particle, which is entering from here. What happens as it enters here? Its velocity is basically in this direction. This is the velocity. I can split this velocity in two components. Okay, what are those two components? One perpendicular to magnetic field, which is that way. This is my v perpendicular. This is my v perpendicular. And one is along the magnetic field, which is my v parallel. Both of them are written here. What are the values of v perpendicular and v parallel? That depends on theta. So this was the direction of magnetic field. Let's say our velocity was making at an angle theta, and theta is, as you can see, it is somewhere between 0 to 90, right? So it is 0 to 90, neither 0 nor 90 nor pi. So we will say that this is nothing but v cos theta. And how much is this? it is V sine theta. Now treat them completely separately. This is V parallel is forming our case 1. Case 1 was when the velocity, which is V cos theta, is parallel to B. What happens? Nothing happens. No force acts on the particle. So particle will go undeviated. So due to this velocity, particle will not experience any force. It will remain moving in this direction, right? With a constant uniform velocity, and that is V cos theta. What about V sine theta? V sine theta is our case number 2, when V is perpendicular to B. So that V sine theta is that perpendicular velocity, and due to that, it will perform a circular motion. Which type of circle? So as the velocity is in this direction, do V cross B. B is in this direction, right? Out of the plane. So force is going to be below, and hence it will perform a circular motion like this. So due to V perpendicular or V sine theta, it will perform circular motion, and due to this V cos theta, it will continuously move in that direction with a constant velocity. What is the resultant motion? The resultant motion is a spring-like motion, right? It will perform the circular motion due to this V sine theta, and the velocity will remain. See, the speed, the perpendicular speed will remain V sine theta, all its just direction will be changing, and this V cos theta will remain same. So it will perform a spring-like motion called helical motion. So here is the helical motion which is going to happen. The particle is entering, and then it is performing both. See, due to this V perpendicular and V parallel, it is performing both circular motion as well as it is also moving forward. So this is the helical motion which particle is performing. Now, there are some parameter of the helical motion which we need to understand. First is radius of the helix. The motion is known as helical motion and the path is known as helix. And the first parameter is radius of the helix. So this radius of the circular motion is known as radius of the helix, and we will say that radius is nothing but radius is coming due to circular part, right? So radius is nothing but mv by qb. But which V needs to be utilized here? The V perpendicular. It is this V perpendicular which is making the circular motion possible, and V perpendicular was V sine theta. So it will be mv sine theta by qb, and that's an expression for the radius of the helix. The next parameter is time period of one revolution. Now, who decide the time period? See, this V cos theta is only deciding, the V cos theta, the parallel velocity is only deciding in how much distance it will move in that direction. Time is still decided by the circular motion. So we'll say for the time period for one complete circular motion is, time taken for one complete circular motion is the time period. So time period is nothing but 2 pi r, that is a distance, divided by the speed. Which is speed with which it is performing the circular motion, that is V perpendicular. And we know that 2 pi by V perpendicular, and r is what? M times V perpendicular, that is V sine theta by qb. Again here this V perpendicular gets cancelled and get 2 pi m by qb, which was same as the time period in the circular motion. Remember the expression was 2 pi m by qb. Here also it is basically independent of the velocity. The next parameter is pitch of the helix. The distance which it travels. See, when the particle was here in one complete circular motion, when it reached this point, the distance it travels, the distance between two spiral is called the pitch of the helix. How can we get the pitch of the helix? So we will be simply saying that pitch of the helix is decided by what? By this velocity as well as the time period. So particle is continuously traveling in this direction with a velocity which is V parallel, and then time is basically a one complete time period of revolution. So we'll be saying that pitch is nothing but V parallel into time period. You can put V parallel as V cos theta and the time as 2 pi m by qb. So once you multiply them, you get the formula for the pitch, and it comes to be 2 pi m by qb times V cos theta. It is better to remember it in this way, that V cos theta times the time period. We already know an expression for time period, that is 2 pi m by qb. So that's helical motion In helical motion, there are three parameters which we found: the radius of the helix, the pitch, and the time of one complete revolution. This is the question, and question says that magnetic force acting on a charge is minus, so I'm just writing Q is minus 2 microcoulomb. So this is the charge on a charge in a magnetic field of 2 Tesla. So magnetic field is B, and that's given as 2 Tesla. Now acting in X direction, so direction is, I'm just writing the direction is I cap, when the particle velocity is that meter per second is. So velocity of the particle is nothing but 2I plus 3J into 10 raised to power 6 meter per second. That's the velocity, and now they are asking us the force. So we can simply apply the formula. Force is nothing but Q V cross B. So the cross product of these two, V and B. So if this is I cap, when I cap, see, it is V cross B. So 2I cross 2I is going to be 0. Then 3J cross 2I. See, I'm just doing this, 3J cross 2I. So how do you do 3J cross 2I? The magnitude is going to be simply 6, and the J cross I is basically minus K. Remember this circle, I, J and K. So J cross I will give us negative K, since we are moving other way around. So J cross I is minus K cap. So it will be minus 6 K cap. Just the product of these two. So I am saying that Q is basically negative. Again, there is a negative sign in charge itself. So minus 2 into 10 raised to power minus 6, because this is microcoulomb. Then V cross B, I am directly doing V cross B. So this cross this is cancelled. This cross this, I got minus 6 K cap. I am writing minus 6 K cap. This 10 raised to power 6 will remain as it is. And this will get cancelled out, and I'll get 12, just positive 12 and K cap. So force is an SI unit, that is Newton. So it is, force is 12 Newton and direction is towards Z axis. Now let's have a look at the question, and this question says the magnetic force acting on a charged particle minus 2 microcoulomb in a magnetic field of 2 Tesla, which is acting in X direction, when the particle's velocity is 2J plus 3I into 10 raised to power 6 meter per second is. So how much is the magnetic force? So we know that magnetic force is Q V cross B, right? So let us just write all the parameters. So Q given is minus 2 microcoulomb. The V vector, the velocity vector is 3I plus 2J. I am writing in order. It is 3I cap plus 2J cap into 10 raised to power 6 meter per second. Right? And the B vector, the magnetic field vector is 2 Tesla in X direction. So I will be writing 2I cap Tesla. Right? So it is 2 Tesla in positive X direction. Now force is basically what? Force is Q V cross B. Now see, the charge is minus 2 microcoulomb. So minus, always put your, in QVB we always put the charge with sign. Okay, so it is basically minus 2 into 10 raised to power minus 6, because that is microcoulomb, not the normal coulomb, right? So V cross B, I am doing, see, when I just need to do V cross B. So for that, I cross I part will be gone. It will be like 3I cross 2I will be 0, because I cross I is 0, right? And J cross I is minus K. So 2 into 2 is 4 and minus K cap, and this 10 raised to 6 I will be getting, right? So this is my force and answer will be in Newton. So let's just check. 10 raised to 6 and 10 raised to minus 6 is gone. This is negative and this is negative. So negative sign is gone. This becomes 8. So 8 Newton and direction is positive K cap. See the negative, this negative sign and this negative sign, I cancelled them out. So 8 Newton towards K cap means positive Z direction. So answer is going to be A. The next question is, an electron of mass m is accelerated through a potential difference of capital V, and then it enters the magnetic field of induction B normal to its velocity. So velocity and the magnetic field, they are perpendicular. So circular motion or part of the circular motion arc is going to happen, right? then the radius of the circular path is, it is a directly formula based question. Let's say radius of the circular path is nothing but mv by qb. M is the mass of the particle given, right? Q is the charge of the particle, which is electron. So charge of the particle is E. I am not writing minus E. So E is just 1.6 into 10 raised to power minus 16 coulomb, because that will decide whether particle will turn clockwise or anti-clockwise, right? So negative sign will simply change the direction, but the magnitude will be E. The B is still B. So this is given, mass is given. But what about the velocity? See, this is velocity, this is voltage. So if you are accelerating an electron by V voltage, then we know that the work done is nothing but Q delta V, right? So when a charged particle is accelerated through a potential difference, then this is the work done, and entire work done will be becoming kinetic energy. So we'll be saying work done is equal to half mv square, where this V is the velocity which we need over here, is equal to charge is Q, which is E, and the V is capital V. So I'll be saying that my V square is nothing but EV by, so 2 EV, this 2 will also by M, and root of that, right? So I'm just putting the value over here. I'm saying radius is nothing but, radius is M by QB and times root of that. So times V, and that is root 2 EV by M. Now just one second, this is also E. Just M will go here and E will go here, and we will get root over, I'm taking everything inside, so this is M square, so 1 M remains, 2 is there, and E square goes here, in the denominator E remains, right? Capital V is still there, and this B will become B squared. So that's the radius of the circular path, and that's it.